Alright, I apologize in advance if this video is a little bit long. We'll try to go quickly. Okay, so this is latent heat is the topic. It's latent heat of fusion or vaporization, and basically they're the same concept. The exact same concept applies in both cases. It's just that fusion applies to melting things and vaporization applies to boiling things, okay? So this would be something that's at its melting point, latent heat of fusion. This is something that's at its boiling point, latent heat of vaporization. What is latent heat? Well, it's the amount of heat needed in order to complete the phase change of the substance without changing its temperature. Okay? So at the boiling point, at the melting point of this ice, right? That ice has a melting point. If it's at its melting point, how much heat is required in order to change it from solid to liquid? And then the other question for vaporization, at its boiling point, how much heat is required to change the liquid into a gas? Okay? So first, if we have the relevant data, so we've collected that in the lab for latent heat, how do we calculate it? And this is the answer right here. Okay? So this would be latent heat as a generic term. If it was for melting, we would call this the latent heat of fusion. If this was for boiling, we would call it latent heat of vaporization. But it's the same formula in either case. Latent heat is equal to this. The amount of heat added divided by the mass. Heat added divided by mass. What mass is it? It's the amount of mass that actually changes phase. So that's that, okay? How does that work? Well, basically, if we want to calculate the latent heat of a substance, we need to know two things. We need to know how much mass changes phase, and then we need to know how many joules of heat energy were added in order to cause that phase change. Alrighty, let's look at an actual experimental setup for how this works. Okay, so here we have a possible method. This is actually the method we will use in class to find the latent heat of fusion. So, here we go. We have a setup here. It's not very great. I made this diagram, so you can blame me for this one. You basically have a heating coil here, represented by this rod. It doesn't actually look like a rod, but some heating coils might look like that. And that's connected by a cord to the power supply, which is just going to be the wall, honestly, for us. So you plug that into the wall. That gives you a source of electricity, all right? And the electricity is going to provide energy, which gets converted in this heating coil into heat, all right? So the electrical energy becomes heat energy, and that heats up the ice, all right? So we've got a lab beaker here. We've got it covered with insulation. In our case, we'll probably just put it on a wooden block to insulate it. And then we've got ice inside there. So that's the setup to start with. Actually, we're not likely to use a beaker. We will probably use a styrofoam cup in order to try to minimize heat loss. Okay, so that's the setup. Heating coil goes in there with a bunch of ice, crushed, hopefully crushed pretty finely, smashed up anyway. It won't be in cubes. And then basically we're going to turn on the heating coil. All right, so you get this all set up. That's the first step. Second step is you turn on the heating coil. So you're going to basically plug this in or turn it on. And then the heat starts flowing. The electricity starts flowing. It heats up. All right, and that heat energy is transferred into the ice and it starts to melt. All right, so you're going to do this for a particular period of time and then you unplug it. We'll be able to calculate later then how much heat energy was added during that period of time to the ice. And that will tell you basically your Q. That tells you how much heat energy was added to the solid form of the thing. All right. Then what? Then you're going to take the amount of water that melted. You're going to carefully, not getting any ice, not spilling any, and getting all the water, you're going to pour it into a measuring cylinder. And then you'll be able to tell from that what volume of water melted, and from that you'll be able to tell how much mass of water actually melted due to the heat energy that was added by the heating coil. Awesome! That is totally cool. So then if you know the energy that was added by the heating coil, you know the mass of water that melted. If you think back to that equation, which I will write down right here once more, latent heat of fusion is equal to Q, the heat energy divided by the mass, then you would be able to calculate this guy, latent heat of fusion. Because we know Q and we know mass. We just calculated both of them experimentally in this experiment. So that's cool. We would be able to calculate then the latent heat of fusion of ice with some error, of course, because this procedure definitely has a bit of error. But every procedure we do in the lab has some error. If we had the proper equipment, we'd be able to use an alternative method, which is capable of being more accurate than this method. So I'll show you that really quick. All right, so this method is a bit more accurate. I didn't go with all of the details of diagrams and pictures and stuff, but you can get the idea. The ice would go inside the funnel, which would have to be a pretty big funnel, and it would probably be clamped on a ring stand or something. So the funnel would go there, and then you would put the ice in there, you'd put the heating coil in there with the ice, and then basically you would let all of it start melting and dripping before anything else happened. So at that point you've got dripping water, drip, drip, drip at some rate, and you might say you might leave it sitting for 30 seconds. See how much water is collected in 30 seconds of dripping with all of it as is, no changes to the setup. And that would tell you the amount of ice that is melting due to the surroundings, right? It'll tell you how much ice is melting as a result of the funnel, as a result of the ring stand, as a result of just the heating coil with nothing attached. Basically, how much ice is melting just due to the heat from the room temperature heat. All right. Then you would find out what that mass is of water, right? And that would tell you how much water melts just due to the surroundings in 30 seconds. Then what you might do is plug the heating coil in for 30 seconds, right? And you'll get more water that drips out. You'll collect that amount of water, find that mass. So then you have, let me do this over here. Mass due to surroundings, right? And then you have mass of heating. Mass of heating plus surroundings, right? So that's the second experiment we do. So if you subtract the mass of heating plus surroundings, if you subtract the first experiment, let's call this 1 and this 2. All right, let's get a little bit more space here. Bam. So this is experiment 1, the mass of the heating due to the surroundings in 30 seconds. And then 2, the mass of water that melts due to the surroundings. That's experiment 1. The mass of water that melts due to the heating and the surroundings. That's experiment 2. All right, so how do we find the total mass due to just the heating? Then we would take, essentially, you would take experiment 1, right? And you would subtract that from experiment 2. And that equals mass due to heating only. All right? So this is the amount of mass that melts due to the heating alone. All right? So this lets you get rid of some of the error of the heat of the surroundings, basically. All right, so there you have another method. Basically, you take this funnel, put the ice in there, melt some water, do a couple of experiments, and you can find out more precisely exactly how much water melts due to exactly the amount of heat you added, and that should give you an accurate measurement of the latent heat of fusion. All right, so really quick, we're going to go through this. How would you find the latent heat of vaporization? So this requires boiling. Basically, you need a controlled situation in a controlled container where you can get the water boiling, and have a way of measuring the water, the mass of the water while it's boiling, and essentially pick an arbitrary. All right, we'll just go through the process. All right, so you have a known quantity of water being subjected to a known quantity of heat for a period of time at its boiling point. So it has to already be boiling. All right. After the time period is over, you have to have a way of measuring how much water is left in the container. So you have to know at the start of the time period, you have to know how much water you had to start with. And then after the time period is over, you have to know how much water is remaining. And if you subtract those two numbers from each other, that gives the mass of water that boiled away. If you divide that by the heat that was added, then you can find the latent heat of vaporization for the water. All right, I use water as an example because basically it's the most commonly used material to figure these things out. All right, so there you have latent heat of fusion, latent heat of vaporization, and the formula that goes with them. And that's the concepts. We'll use this in class. That's all I've got for you, and we'll see you next time. Thanks.